11. So we're looking at these last couple. We're also still in chapter 8, so it's the last half of chapter 8 in your textbook as well. I just split it because it's a lot, okay? So it's still series, so we're still using series, but we're not really doing any of our convergence tests anymore, which is why I feel like it's kind of a nice natural break as far as we did all the conversion test stuff. And now we're actually going to kind of look at like applications of series, or like what we can use series for. So, first, let's remind ourselves, what is a tangent line approximation?
Using the tangent line of a value to find a value very close to the original.
Okay, and what is the equation for that?
L of x. I don't know how you would term it necessarily.
Okay. Do you remember what we used?
Derivative?
We used the derivative, yeah, at some c value, right? Like, because we're choosing a c value, a lot of times it was like 0 or 1, yes? And then we would calculate something that was close to that c value, like 1.2 or 0.1 or something like that. Okay, so we have f prime of c times x minus c plus f of c.
Yes.
Yes or maybe? If c is the value that we were using originally to help us approximate whatever it is that we want to plug in for x. Yes, no, maybe. Yeah. And remember that then we kind of took that a step further, yes, with our Euler's method. Do you recall that? Where we said that then I could take that tangent line approximation and build off of that a new tangent line approximation so that I could get a little bit further out to something that wasn't quite linear. Yes? And remember, we kind of added to it each time. Agreed? What have we been doing in here that adds a bunch of things together? Summations or series. And so basically what we're going to create now is this idea of, notice like what degree is this function? It's a tangent what? Line, which is a degree of 1. But do many of our functions work in a, or do look like a line? No, like 98% of them don't, okay? And so what our series is going to allow us to do is to build out other, which is why it's called Taylor polynomials. It's going to allow us to build out things of other degrees to approximate functions. Are we all with me there? Yes, no, maybe? At least the overall goal, right? So it's similar to a tangent line approximation, but it's going to allow us to approximate things that aren't necessarily a line or look like a line. So what would the tangent line approximation be here at x equals c? Yeah. So like if I wanted to find L of c. Yeah, right? So if I plug in c here, what do I get? 0. So I just get f of c. Agreed? So do we agree that my approximation is like the exact value when I'm at the value that I used to begin it at? Yes? It will also have the same slope as well, right? So my, let's put my slope of L of x, yes, is equal to the slope of f of x. Agreed? At c. Yes, no, maybe?
Yes.
Okay. And this idea is kind of important because it allows us to what we're going to call center our functions. Okay. Meaning that we're going to have to pick some value. just like before, a lot of times we're going to pick 0 or 1. It's going to be nice whole numbers to center it at. But we're going to use this fact that I know that those y values and those slope values are then the same thing. Yes, so maybe so. Are we all kind of okay with the idea of what we're going for here?
Yes.
Alright, so let's look at what this looks like. So right here I have cosine. Yes? Is cosine a linear function? No. Is it really close to a linear function anywhere? A couple places, right? Like I could, right, like at pi over 2, yes, or like 3 pi over 2, we could kind of get those to be linear, yes? The problem is that do they stay that same linear direction the whole time? No, we're like switching. Agreed? So let's first just make the linear approximation that we would want to start with. Okay. So it says find the equation of the tangent line of y equals x. Y equals cosine of x at x equals 0. So what do we need in order to write the equation of the tangent line? Broader. What are the two things that I need to write the equation of any line? Point and a slope. Okay. So yes, I need my derivative because my derivative will end up being my slope. What's my point there? 0, comma 1, right? So cosine is 1 at 0. Agree? Okay. What's our derivative at cosine? Okay. So then if I plug in, what do we get for my slope? Yeah? So my slope is 0, what do I get? Y equals what? Just 1. Yes? Are we all okay with that? So what does that look like? So everything is next to this sketch. What kind of line is that? Okay? Horizontal line. Specifically at 1. Alright, is that a very good approximation for my graph?
No.
Not a whole lot. Alright, so it says notice that our approximation has the same y value and slope as our original. What other property can be used so that it matches at x equals 0? So like what's wrong with it right now?
It's not curvy.
Cool, okay. How do we describe curviness in calculus?
Parabolic.
Just the general term.
Concavity.
Concavity, right? So right now our concavity is not matching. Yes? Would we agree with that? Because it is not curved. And the curviness for us is what we call concavity. Am I curving down? And how much down are we curving? Or am I curving up? And how quickly are we curving? Yes? And how do we determine concavity? The second derivative. So what degree would we need in order to make that approximation work? A second degree, yes. Are we all okay with that? That again, we're trying to build this idea of a linear approximation, but I want to make my linear approximation more accurate, which means that instead of a first degree approximation, I want a second degree approximation. Yes, no, maybe so.
Yes.
Okay. So we're talking about a quadratic going to be a degree of 2, it's going to be a quadratic approximation?
Yes.
Are we all okay with that idea? So what might that look like? So instead of L, okay, because L stood for linear approximation, right, which doesn't quite fit anymore because we're now talking about a quadratic, okay? But we also don't want to use a Q because think about, again, the overall goal here is to build out as many as we need, yes? And I have a quadratic, what comes after quadratics? Cubic, after that, we don't have special names, yes? But we can classify them all as polynomials, yes? So instead of trying to use like specific letters now, we're just going to use P, but we're going to use a subscript of 2 to indicate that I'm now looking at the second degree. Are we okay with that? Because now I can look at P sub 4, P sub 15, P sub whatever, and I don't have to worry about it. So your linear approximation is actually just a P sub 1. Yes, no, maybe.
Yes.
Okay. So what do you think that's going to look like? We said that really I'm just adding on to what I already had, correct? So we're actually still going to start with a linear approximation. Now I am going to change the order of it a little bit just because of, since I'm going to build on from here, okay, I am just going to change that, put that f of c up front. Are we okay with that? It's just addition and subtraction, so I can write it however I want. So plus, and then remember we had that f prime of c times x minus c. So that is still like the first part of that. Yes, no, maybe.
Yes.
But in order for it to be a second degree, we also said that I have to have a degree of 2 somewhere, right? Okay. And I still want it to be centered around this idea of x minus c, right? I still want it to be centered at c. Are we all okay with that? So my plus here, I still have an x minus c, but now we're going to raise it to the second power. And we said we want what to match?
Concavity.
We want the concavity to match, yes? And we said our concavity is the second derivative. But if I'm wanting my concavity specifically to match at c, what would I write to represent that? So if I had f prime of c, right, that meant that my slope of c and my slope of my approximation were equal. So then what would I have to have here?
F double prime of c.
There we go. We are okay with that.
Yes.
Now it is a little bit trickier because I have a second degree polynomial here, yes? So when I take the derivative of something, what do I get if I have an x squared? A number, right? Specifically if it's x squared, what's in front? Take derivative of x squared. I get a 2 in front, right? There we go. And so we need to kind of undo that 2, okay? Because I don't know if there was a 2 at the beginning or not of my actual concavity, yes? So to undo when I bring down this 2, okay, I need to have a 1/2 there as well. Now if you want to go through all of the steps of like actually, like you can take the derivative of this thing and put an a value there and solve for the a value to figure out why that's it. You get a little lost in the algebra, so are we all okay with me just saying I need this 2 to go away when I bring down the 2, so that's why I need a 1/2 there. Okay. To me that just makes more sense, just like thinking through it than trying to like solve all of this stuff out. Yes, no, maybe so. Okay. So now let's find the quadratic approximation for f of x equals cosine of x. So what are the things that we kind of need then? We need basically our y value at c, our derivative value at c, and now we also need our second derivative at c. Agreed?
Yes.
So I already have my original function, so to me it kind of is helpful if we just kind of go down. What's our derivative here? Negative sign. So then what's our second derivative? Are we okay with that? So then f of 0, because again we're centering at, I should have put that on there, centering at x equals 0. So f of 0 gives us 1. F prime of 0 gives us 0. And f double prime of 0 gives us negative 1. Are we okay with that? Okay. So then let's build out our function. So I have p2 of x equals, what's going to come first? Our f of c, which we said was what? 1. Okay. And then I'm adding, yeah? And I'm adding f prime of c times x minus c, but what is f prime of c? 0. So that part's just going to kind of go away. We're okay with that. So then I'm still adding. This time I'm looking at f double prime of c. Okay, what is f double prime of c this time? Negative 1. But what did I also say we have to have there? Divided by 2. So 1 times what? X minus our c value here is 0. I'm going to write it out just so we can kind of get the idea of it, because it won't always be centered at 0. Are we okay with that?
Yes.
So now if I do a little bit of simplifying. I get 1 minus 1/2 x squared. We're okay with that. That's no maybe. So going backwards now to my original, what would 1 minus 1/2 x squared look like? It's going to be a what? Parabola. It has a negative leading, or if I rewrote this, a negative coefficient, right? Which means it's going to be facing down. I also have a 1, which means that it's been shifted up 1. So I have a vertex at 1. Okay? And I have a 1/2, which makes it a little bit wider. Yes? No, maybe? A 2 would make it skinnier. Okay, it's not going to quite meet if you were to actually like graph this on Desmos. Okay? But now, are we looking closer to what I have there? Yes, no. For this area. Yes? Okay.
Yes.
Because does it really match very well after that?
No.
Not really. But what might we do instead? Add more degrees, right? Because if I look at this type of thing, what does that kind of look like? A cubic, right? So, in general, we can add as many polynomial degrees as we need and or want. Okay? So that is called an nth degree Taylor polynomial. Okay. So if f has n derivatives at x equals c. So again, we are centering, okay? You're gonna hear that word a lot, so that's kind of why I stress it. We are centered. Because we're gonna get to intervals of convergence later on, and we're gonna need to know that center. So it's a good way for us to kind of start thinking about it in that terms. Then we have this, again, polynomial that we can use as an approximation. So we start with f of c plus f prime of c times x minus c plus, and technically what we were doing there, without actually knowing it, is we actually have to use factorials here down below. Just because of the way that when we take our derivative, we have n powers there. We're going to bring that down however many times we need, which ends up being a factorial instead. So we worked it up to here, okay? But in general, I can go out as many times as I need, right? Where it's the, so remember this stands for the nth derivative. So however many derivatives we need, divided by n factorial times x minus c to the nth power. This is called the nth degree Taylor polynomial. Okay, it's named after Brooke Taylor, who was an English mathematician. Now we were specifically looking at if c equals 0, okay, and in that case, basically our x minus c's end up going away. So we get something that looks like this. This is specifically called a Maclaurin polynomial, and it's named after Colin Maclaurin, who was a Scottish mathematician. But you don't necessarily have to remember that it's a Maclaurin versus a Taylor, because they do the same thing. So like a Maclaurin is just a specific case of a Taylor polynomial. Kind of like a square is a specific case of a rectangle. Yes?
Oh, I see.
But if I remember my general formula for a Taylor and then I just plug in zeros, I get the same thing. So you don't necessarily have to remember the separate one. It is helpful to remember that the Maclaurin is centered at 0. Yes, no, maybe. Ready to look at something a little bit more fun then? We went to degree 2. Do we want to? And we said that that wasn't like bad, but it wasn't great either. So we're gonna go to a higher degree. Well, maybe. The biggest things with these is not necessarily that they're hard, right? It's like derivatives and plugging in stuff, right? The thing that we probably have seen the least are just the factorials, right? But as long as we've dealt with them a little bit now, which is why I had us practice last unit, it's just remembering that those are multiplication, yeah? Okay, but the biggest thing is kind of like with our Euler's method was not necessarily that any of those pieces were hard, it was just the organization of everything, right? Keeping track of our derivatives and then plugging in whatever you're centered at. Yes, no, maybe? Which is kind of why, if you notice, when I did it here, sorry, go back 2, 3, 4. I don't know where I had it. Where did I have it? There we go. Right, I kind of set it up as like starting kind of a table, right? Like I had my original function, my derivative, my second derivative. I could have kept going, and then in the second spot is where I kind of started plugging in my stuff, right? So kind of table-ish looking there. Are we okay with that? Which just makes it easier. You don't have to organize yours like mine, but you need to come up with some sort of organization and not just put like things everywhere. Yes, because it can get really easy to like mixing things up if you don't have some sort of organizational. Yeah.
Is there a way to do this in a calculator? Like get like a 6th degree?
Like make the calculator do it for you?
Yeah.
Not really. So if we wanted to write a 6th degree, speaking of 6 degrees, we got to figure out what's going on here. Okay. We can kind of ignore these headings. The like thing that I used does it in a little bit of a different process, but I think it's more confusing to do it that way. So we're just gonna kind of ignore those and just make the table. Okay. So we said our original function was what? Cosine x. Yes, no, maybe. And we're centering at x equals 0. And we said, so this will be my functions, this will be my evaluator. So evaluate. You don't have to label them as long as you know what you're doing, right? And we said that cosine of 0 is what? 1. Okay. And then what's our first derivative of that? Are you okay with that? Okay. What's our second derivative? And our third derivative? Positive sign? Are we all with me up until that point? Fourth derivative? Cosine? And then what's going to happen after that? Negative sign is just going to keep repeating itself, right? Negative cosine, and so forth. Yes? Alright, so then what is negative sine of 0? Negative cosine of 0. Sine of 0? Cosine of 0. Negative sine of 0. Negative cosine. Yes, no, maybe. We're okay with that. What's going to happen here, though, when we start plugging into that polynomial? Remember, I'm using, we can't really call them slopes, right, because it's not a linear function, right, but it's in front of each of our x values, yes? So if I'm multiplying each of these by x squared, x to the third, x to the fourth, what's going to happen? They do repeat. More specifically, what happens every other term? They equal 0, right? So I'm not going to have that term. So we say that our 6th degree Taylor series is going to start the same way. So 1 minus 1/2 x squared. I would technically add what next? The third derivative, but what do we give for our third derivative? 0 again, right? So then we end up adding our fourth one, yes? So it's going to be what? Is it 1/4? What's 1/4? Remember, what did we say we technically have there? Factorial. Alright, does anyone know what 1 over what 4 factorial happens to be? It is 24. And then I'd have, again, we're centered at 0, so usually we would have x minus c to the 4th power, but we're centered at 0, so I just have an x to the 4th. Yes? Okay, and then what happens to my 5th term? Goes away. So then my 6th term is going to be negative this time, so I would have minus 1 over 5 factorial times, 6 factorial. Skip our 6 factorial times x to the 6th. There's no moving. Or if we wanted to write this out, 1 minus 1/2 x squared plus 1 over 24 x to the 4th minus, does anyone know what 6 factorial is? 720 x to the 6th. Yes, no maybe? So do we want to look at how close we are now?
Yes.
So I am looking at this, if I can get it to, it's not what I want. There we go. Yes, no, wait. This is our cosine of x. And we started with 1, right? Which we said it's not great. Minus, and then I added in my, not 1 half x squared, which helped a bit, right? It just wasn't quite as wide as we needed. But then next up we added in our 1 divided by 24 x to the 4th. Are we getting closer? Yeah. Then next up we had a minus 1 divided by 720 x to the 6th. Are we getting closer? Okay. What would happen if I wanted to add another term? I get closer. Okay, what would our next term have to be? To the what power? 8th, right? Because if I took the 7th derivative, we'd be back to a sign, which is going to be 0 again. What do we notice about the SIG in sign of all of these? They're alternating. So I have a plus. It would be 1 divided by 8 factorial. Yes. Times x to the 8th power. Right? And we could keep going if we wanted to. But do we notice how that, like, as I add on each piece, I get closer and closer to what the full thing is? Yes, no, maybe? Which I think is kind of cool, right? Like, that we can now build out these, like, polynomials that, like, can get us pretty close to whatever our function is. Because notice that, like, plugging in a value to this is fairly straightforward versus plugging in a value to cosine, right? Which we don't know what the cosine of 2 is, yes? Or the cosine of 3.5 or something like that. So it's easier to plug stuff into a polynomial than it is a trig function. Agreed? Also, what's nice about polynomials, like for calculus stuff? They're easy to take the derivative of, they're easy to take the integral of, right? Like they have easy properties that I can just plug and chug a power rule, yeah? So they also give us easier things to deal with when I'm wanting to take antiderivatives and derivatives. So instead of dealing with the original function, sometimes it's easier to deal with the Taylor approximation instead. Are we all okay with that? Yes. Okay. We'll stop there for today. Tomorrow we'll look at a little bit more of like how we build Taylor polynomials of other things, okay? As well as our 3 special Taylor series that you need to know, which are sine, cosine, and e to the x. Questions on any of that?
Is there a way to write a Taylor approximation in summation notation?
Yeah. So later on in this chapter we have Taylor series. So that's what we're gonna do then.